All right, I'm gonna start letting some people in and just tell them to wait 5 minutes for everybody to get here.
Yeah.
What's up, everybody? Thank you for coming out. Thanks for being here. This is our second workshop for Apply ML. We're gonna wait a few minutes just in case we have any late people jumping. Question in the chat from Apoorv. Can you guys share the slides from last week? We didn't actually have any slides last week. We had like a few introduction slides that really weren't too relevant. I'd encourage you to check out our YouTube page where there's a full recording of our workshop from last week. Because we primarily work directly in Jupyter notebooks. So I'd recommend you go check out our video of our workshop. That includes our full Jupyter notebook on our YouTube page.
Some people are still trickling in, so we'll just give it another 1 or 2 minutes before we start. Sorry about that.
All right, I think we're gonna go ahead and get started. It's 7:05, so thank you guys to everybody, or thanks to everybody for being here. We're really excited that you guys enjoyed the first workshop and came out to our second one. So this workshop's format is going to be a little bit different than last week's because in this one there's just a little bit of information we want to go over before we dive into the code itself. So let's get started. By the way, today's attendance code is the study. Um, I think most of you guys here are freshmen, so you guys won't know what the study is, but the study is this takeout place that we have on the hill. They have sandwiches, salads, make your own pizzas. One of my favorite places to eat. And when you guys come back to campus, make sure to check it out. Awesome. So you guys might remember this slide from last week's presentation. We talked a little bit about the ML trading pipeline. So last week, we pretty much covered the data validation and the pre-processing parts of this pipeline because we took our raw Titanic data and we cleaned it out. We added in some features. We took out null data, we took out missing data, and we cleaned up the data and then we saved it into a new CSV to be used by our model. So today we're going to be going over the first part of the next step of this pipeline, which is model training. So model training, in my opinion, is the real fun part of machine learning because this is where you create a model. This is where you feed the data into the model and then see how the model did, right? This is really the nitty gritty of machine learning, and there's a ton of different models that can be used to train data. Do you guys know what types of models are used? And if you have any ideas or have heard of any potential ML models, would you mind putting them in the chat right now? Aryan says neural networks. Yep, that's a big one. Linear regression. Yep, logistic regression. Brian just said that. Awesome. CNNs, convolutional neural networks. Awesome. Any others? GANs. Yep. Random forest classifier. Absolutely. Any more? There's like two more I'm looking for. KNN. Yep, that's one of them. KNN is K nearest neighbors. RNNs. Yep, that's another. So there's one more I'm looking for. It's closely related to Mason's answer of random forest. Well, the last one I had in mind was decision trees. Yep, Christine, absolutely right. Decision trees. We'll be going into that in one of the future workshops. For today, we're going to be talking specifically about logistic regression. So let's get started. Cool. So before we talk about logistic regression specifically, I want to zoom out a little bit and talk about linear models as a whole. So two examples of linear models are one, logistic regression, and two, linear regression. So with a linear model, what we're trying to do is we're trying to take our data and essentially fit a linear line that will best fit our data and predict outputs of our data from the given inputs that we have. So think of a linear model as say like y equals mx plus b, right? And you're given some x, which is your input, and you want to predict some y, which is your output. In our case, all of our x's are going to be all our training data that we cleaned up and used last week. And in our case, the y, which is the output, will be whether or not somebody survived. So the thing about a linear model though is that, as it says in the name, is it's linear. It's very, very simple. It can't map very, very complex functions because, of course, it can only go in a straight line. If there's any curves in your data, or maybe your data would be best be modeled by something that can model curves, or say a cubic function, a linear model is not going to be able to handle that. A linear model is pretty much the most simple version of a model that we have because it can essentially only create a straight line and then decide and predict off of that straight line that it creates. Awesome. So let's talk a little bit about what a hypothesis function is. So in this case, we have a linear model, like I've been saying, and what our hypothesis function is going to do. So on the left side, if you see h of x1, x2, all the way to xn, right? So x1, x2, xn, those are all of our features of our data. So if you guys remember from last week, we had a lot of features in our data set, right? For example, what cabin somebody was on, what the price of their ticket was, right? Whether they were a male or a female. Those are all different features that our model is going to take in. and then we'll create a hypothesis function out of those features. And that hypothesis function you can see on that right side will be W0 plus W1 x1 plus W2 x2 all the way to Wn xn. So let's talk about these W's and these X's. So X1 through Xn are different features. So just like I mentioned, you know, the sex of a person maybe, or the price of their ticket, or what cabin they were in. W1 through Wn are the weights. So like it says on the slide, these are the learnable parameters of the model. So what this means is that the model is going to look at all the data we have and then try to decide what the best values are for W1, W2 through Wn, so that this equation we have up here, this hypothesis function, outputs the correct answer as much as it can. So essentially what we're trying to do here is we're trying to take x1 through xn and then multiply all of these x1 by xn by some weights, which are w1 through wn, right? And then using this multiplication and summation, create an output prediction, which will tell us whether or not somebody survived. Okay, I'm going to pause right there for some questions because that was a lot of information. If you have any questions, feel free to throw it in the chat or just to come off mute and ask. If you want me to explain something again as well, feel free to say that as well. Awesome. So let's finish out what we have left on this slide. So as you see in that last bullet point, when you change weights, we essentially alter the hypothesis and the output. And when we alter the output, that's altering the predictions. So we're trying to change the weights and tune them so that our predictions are as accurate as possible. That's what we're trying to do with our linear model here. Awesome. I'll hand off now to Varun for a quick logistic regression explanation.
Right. Thanks, Harsh. So, if you noticed in the previous setting where we had linear regression and we were predicting some linear combination, our output was some linear combination of all our inputs, but that would result in a continuous output. So what that means is you could pretty much have your output could be pretty much any value between minus infinity and plus infinity. But of course, in this setting, for example, where we worked on last week with the Titanic data, we want to predict the probability that someone survived or didn't survive, and we want to make a binary classification. It's either 1 or 0 for every single person. And of course, in that case, linear regression doesn't work exactly. We need some method to convert this continuous output into a probability measure. And we still want to use a linear model that's relatively simple and can capture the information from the data, but still make a prediction instead of a binary output. So in this case, we use logistic regression. And how exactly does that work? So does anyone want to take guesses about what kind of classification tasks are commonly done? Once again, throw your answers in the chat or unmute yourself and give an answer if you want. Right, the slide should be in the chat. Okay, sure. I mean, some of the simpler classification tasks are maybe you want to classify tumors into benign or malignant. And so obviously you have a lot of applications in the medical imaging sector. Numerical digits, I'm sure a lot of you who use iPads or other devices might know how the stuff you write on the iPad automatically gets converted to text. And this is, of course, built on some machine learning model that converts the letters and numbers you write into text. So this is, again, very useful. Right. So that very classification can be used in a lot of different settings. And let's see how we would go about that. So in any classification data set, you would have like you could have some kind of input. In our Titanic data set, it was just a bunch of features that talked about like the price of a ticket, what class of cabin you were in, and so on. In an image classification task where you want to identify whether every image is a cat or a dog, it could just be a bunch of pixels for every image. And maybe for tumors, once again, you have images, you want to classify it into benign or malignant tumors, and so on. So if we try to plot logistic regression in some sense, we have maybe our input data, or the x-axis. Of course, we work with many more variables, so it's not easy to plot it, but the idea is still the same. Maybe you have some kind of distribution like this, where smaller tumors correspond to a non-malignant tumor and larger tumors correspond to a bigger tumor. So the idea is that we somehow do linear regression like this and say that if the linear model predicts a very high number, then we're going to convert that to a yes and say that we're going to predict that this tumor is cancerous for high values and smaller values for no. And after that, we convert it to 0 or 1 based on some rule. So what exactly is this rule? This is the idea of a decision boundary. So basically, you want to have some kind of linear line that separates your data, and then you want to have some kind of rule that determines what how you classify points into class 0 or class 1. At this point, don't worry if you don't completely follow the explanations. This theory is just to give you some kind of motivation for what the code's going to look like. You can, of course, explore this theory in greater detail, and we will be teaching it in our beginner track workshops. But for this workshop, all you need to understand is get some kind of intuition for what exactly the logistic regression is and have a feel for how it works. You don't necessarily need to know all the details behind it. So at this stage, are there any questions about what we're trying to do? Cool. So let's go ahead. So what we're going to say is that we're going to convert the output, so the weights, into x, which is our data, and we're going to apply a function g to that so that we get the probability of belonging to a particular class. Don't worry too much about the notation, but that's basically read as probability that that particular example is 1, given whatever values of x we have for that particular example. So all this is saying is that if x has certain values, the price of a ticket is $7, the person is in cabin 3, and then you combine that, you use your weights and say that maybe this person is unlikely to survive, or maybe this person probably did survive. So G essentially takes care of this. G is the sigmoid function. And if you see it, the function looks really nice. Basically, G of 0 is 0.5. And as x tends to infinity, G of x tends to 1. And as x tends to minus infinity, G of x tends to 0. So now this is a very cool property, simply because it helps us convert any sort of continuous output to a number between 0 and 1. So, and we can interpret this number as a probability. So for example, if your linear model outputted something like 500, and you convert that and you put that into a sigmoid function, right? 1 over 1 plus e raised to minus 500, that number would be very close to 1. And so we would say this person probably has a very high probability of surviving, and probably did survive. If on the other hand it was something like negative 100, this probability measure would be closer to 0, and we would predict that this person did not survive. So what we're essentially doing here is just a modification of linear regression. We're trying to convert the continuous output of linear regression to a number between 0 and 1. And following that, we say, okay, if anyone has a probability of greater than 0.5 of surviving, let's just say they did survive, or less than 0.5, they did not survive. We can, of course, vary this threshold. It doesn't necessarily have to be exactly 0.5. we could say we're only going to predict that someone survived if the probability is greater than 0.7 or 0.8. That's completely up to you guys. Typically 0.5 can work well, but depending on depending on what your data looks like, you can vary the threshold as well. Right. So this is essentially what I just covered. Don't worry at all about the notation. As long as you have an intuitive idea that you have a bunch of weights, you get a number from minus infinity to plus infinity, squeeze that in between 0 and 1 to get a probability, and then make a prediction based on that. Right. So once again, I'm going to take I'm going to pause for a second and ask if there are any questions. Guys, at any time, even if I'm speaking, if you want to throw in a question, that's perfectly fine.
Yeah, guys, let's just do like a quick survey. So on a scale of 1 to 5, with 1 being I've absolutely no idea what's going on, and 5 being I'm a logistic regression expert. Can you guys drop a number in the chat just to give us an idea of how much you guys are following and what you guys understand? All right, we're getting some 2s, some 3s, some 4s, some 3s. A lot of 3s, a lot of 4s. Some 2s. Okay, that sounds good. We were hoping that after this, you guys would be somewhere around a 3, because our goal is just to give you guys a very high level understanding of what's happening with logistic regression. We don't expect you guys to understand the nitty gritty of the math, because that's Intertrack's job. We're just trying to teach you guys the applications. So I'm seeing a lot of 3s, some 4s, some 2s, and we're pretty happy with that. If you feel like you're at a 2 or a 1 and you have some questions, please feel free to ask so we can understand what you guys don't understand and go into a little bit more detail on
that. Yeah. So once again, just to summarize what we've done so far, given any kind of input, right? Like we saw exactly in last week's data, we have a bunch of different features. We have price of a cabin, we had cabin class and so on, 5 or 6 different features. And what we're going to try to find is a set of good weights. Don't worry right now at all about how exactly those weights are calculated. The Python code will do that all for you. But the idea is that you can find these set of weights that essentially combine with the data input and give you some kind of output. So you're basically just trying to find a linear model, exactly like how you do y is equal to mx plus b. If you have a bunch of points on the xy plane and you try to find a best fitting line, that's exactly what you do. And you say that the high values correspond to one class, the low values correspond to another class. And the way you quantify that is by saying that I have outputs from minus infinity to plus infinity. I'm going to squeeze that value between 0 and 1 by using the sigmoid function, g of x. And after that, you're going to say, okay, if the probability is going to be greater than 0.5, predict one class. Probability is less than 0.5, predict another class. Don't worry at all if you still don't get it. I'm sure once you start trying the code, it's going to be a lot easier. But yeah, definitely, this is something worth spending time on. So it's not something you get at you understand completely the first time you're exposed to it, but eventually we all understand it. So yeah, no need to worry too much about log of odds. This is some of the more theoretical parts about logistic regression, but we don't need to go over that right now. So all you need to know is that inbuilt Python uses something called gradient descent to find those optimal set of weights, but you absolutely don't have to implement that yourself. You can if you want to, it's a fun exercise, but in practice, you're never expected to write these algorithms from scratch again. And yeah, I guess the last thing to cover is that in linear regression, right, when you're trying to fit a bunch of lines, you try to minimize the mean square error. And in logistic regression, you do something similar. I know this equation looks quite scary, so we're going to break it down for you. So suppose someone did survive, right? That means their output is going to be a 1. Um, so for example, their output is going to be classified by this y. So if they survive, y is going to be 1, and 1 minus y is going to be equal to 0. So the second part of this term completely vanishes. And so ideally, if y is 1, we want our prediction of the probability a to also be pretty close to 1. And if you know, if you're familiar with the logarithm function, you know that log 1 is pretty close to 0. So what that means is, if y is 1 and your prediction of the probability is also close to 1, then this term essentially becomes very close to 0 and your entire loss becomes 0. On the other hand, if y is 0, right, uh, then then the first term becomes 0 and the second term becomes non-zero. Uh, and basically what you need to understand about this function is that if you try plugging in a few values, you'll see that if the true class is 1 and your probability estimate is also close to 1, then this loss function is going to be very small. If on the other hand, your prediction is very different from what the true value is, this loss becomes very large. And so inbuilt, what Python is going to try to do is make this loss as small as possible. You can think of it intuitively as just minimizing the mean square error, like how it happens in linear regression. This is just a similar function for logistic regression, and it's more convenient to write the loss in this format instead of this format. But you can intuitively think of it as the same thing. It's just trying to say, if your prediction is very different from what the real result is, penalize your model and change the weights. Um, right. Once again, are there any questions about what we're doing so far? Okay, so does everyone understand? Okay, so let's take a quick poll once again. 1 to 5, you know exactly what A means. That's 5, and 1 is you have no idea what A is.
And just want to answer Jacob's question, is gradient descent only used for logistic regression or linear regression as well? Gradient descent is used for logistic regression, linear regression, and neural networks. So it's used across the board in a lot of different models.
Right. So the question was once again, do you guys understand what A and Y is? So Y is essentially the actual class, like 0 or 1, whether the person survived or didn't. And A is your model's estimate of what the probability is that that person survived. And once again, just to recap, what this function means is that if your probability estimate is close to what actually happened, then your loss is going to be very small as desired. And alternately, if your prediction varies wildly from the true probability, then this loss function is going to shoot up to infinity. So what does y mean again? Y is the true label of whether or not someone survived. So it's going to be just 0 or 1. And your model is essentially just trained on that. So it's going to try to make your prediction of the probability as close to y as possible for all the data points. So the idea behind this, of course, is that you have a bunch of data that's visible to you. So you have data, and you have all the features, and you also know whether these people survived or not. And then the idea is that once your model is trained on this data, you want to make predictions about other people who you don't necessarily know whether they survived or not. So that's basically saying that I know, I have some information about these people. I also know their outcomes. So now, just using just the information for other people, can I try to think about what their outcome would have been? So that's the intuition behind what we're trying to do here. So we have a question. So A can be a value between positive and negative infinity, not just a 1 or 0, correct? So not between positive and negative infinity. Like we covered before, after the linear regression stage, your output could be between minus infinity and plus infinity. But then after you apply the sigmoid function, you basically squeeze that minus infinity to plus infinity range between 0 and 1. So A can be anything between 0 and 1. So it's just a probability, right? So it has to be between 0 and 1. Do we have any other questions? Cool. Let's go ahead. Just try to figure, like, you can always play around with this function a little bit to see what happens when y is 0, what happens when y is 1, and so on. After a little bit, it's easy to build some intuition for what this function is trying to do. Don't worry about this.
Okay, wait. Real quick before we get to the code itself, Varun, do you want to go back to one of the first slides? I just want to give like a quick high-level summary one time before we get into the code again. Yeah, keep going back. Looking for, I think, slide number. Yeah, I'm looking for slide number 10. Just logistic regression model is what it's called. Yeah, there we go. Okay, and do you want to get the text on there as well? Awesome. So just wanted to give a quick summary of logistic regression from the top. I know we've given you guys a ton of information in the last 20 minutes. We're going to get to the code in just 2 minutes. I just wanted to give a quick summary just to kind of recap everything we've talked about in the last half an hour. Okay, so with logistic regression, what's going to happen is we're going to take in a bunch of inputs, which is going to be all of our features. So like I said, the price, the cabin, the gender of the person. And then we're going to feed this into a linear model. So if you guys remember on one of the first few slides, we had x1 times y1 plus x2 times y2 plus x3 times y3. So we're going to have an equation like that. And that equation is going to give us some output. So imagine that equation's output being somewhere on this green line, which is on the screen here. Then if that output is above 50%, we're gonna mark it as a yes. So if you see like the red X's on the top, we'll mark it as a yes. If it's below this 50% decision boundary, we're gonna mark it as a no. Then we're gonna go ahead and do this for every single piece of data we have and then see how we did. If we did very well, we're gonna keep the model as it is. If we did badly, we're gonna readjust those weights using gradient descent and cross-entropy loss and then try again. So we're essentially just gonna iterate and keep trying and keep trying and keep trying different combinations of weights until we come upon a model which gives us good results. And in a sense, that's kind of a small picture of what machine learning is. You're trying a bunch of different combinations until you get something that works. So once we get something that works, that's when we go ahead and validate, and that's when we go ahead and see how our model actually performed. Okay, so once again, quick high-level summary. We're going to take all of our data, we're going to input it into a model. We're going to have the model make predictions. If the model does well, we're going to keep the model as it is. If the model does badly, we're going to go back into the model, change the weights of the model until the model does well. Awesome. So can we get in the chat again, 1 through 5? How do you guys feel about the quick high-level overview of logistic regression? Do you guys have some sense of what is going on? Awesome. Lots of 4s. Awesome. That is great to see. We love to see the 4s. I think we were at lots of 2s, 3s, and 4s earlier, and right now I'm consistently seeing a lot of 4s. That is awesome to see. Cool. But of course, you guys didn't come here to learn theory. You guys came here to learn code. So let's go ahead and jump into the coding portion of this workshop. Varun, if you could jump to the last slide really quick. Awesome. So if everybody could go to this link, this will link you to a collab notebook similar to the one we had last week. And if you guys remember what we did last week, we downloaded the notebook, then we went to Google Colab and uploaded the notebook. So if you guys could just go through the same steps that we did last week, Varun will work through them on the screen right now, just so you guys get a quick reminder of how we did that. That way we can all have the Colab notebook and start with the code. And we'll give you guys about 2-3 minutes to do that. So go ahead and do that, and then we'll check in soon. And if you have any questions in the meantime, feel free to put it in the chat or just shout it out on Zoom.
Cool. So for this notebook, we're going to be doing essentially the same thing we did last week. In case someone wasn't there last week, I'm going to go over how we're going to use the notebook again. So essentially, open up the link. What you want to do is download this file. My Wi-Fi seems to be a little slow. Cool. Once you have the file downloaded, go to colab.research.google.com and what you want to do is go to File and click on Upload Notebook. Once you go to Upload Notebook, choose the file that you just downloaded. It should just be in your downloads. Click on that and open it up. Right, so we're just going to give it a couple of minutes until everyone's done with this. Just drop a message in the chat once you have the notebook open. Does anyone have any problems with opening the notebook? Right. So once again, were any of you not there last week? If you don't feel comfortable messaging on the sending a message to everyone, you can always personal message me or Harsh. Okay, cool. I think most people should have the notebook open. Let's get started then. So once again, when we're using a notebook, we first need to import all the libraries that we need. And this is basically just a bunch of code that that's probably going to be useful for us. The main thing that we're going to be using this workshop is logistic regression from something called sklearn or scikit-learn. So Python essentially has this library called scikit-learn that implements a lot of machine learning models for you. So all that stuff we covered about how logistic regression has a bunch of weights, we convert it to a probability, and then finally make a prediction. Python essentially handles all of that for you. So what you essentially need to do is provide the input data X, all the labels Y, and let Python work its magic. Right, so let's go ahead and get started. So just run the first cell. The first cell always takes a little bit of time to run. Right, and if you guys remember last week, after we after we finish cleaning all the data, we save that file to our Google Drive. And what we're going to do this time is import that very same data back into our notebook. So what you want to do is essentially run this cell, and it's going to send you to another link. Try to use the same account that you used last time. Uh, Copy this link back over here. And this should give you access to your Google Drive. This is going to take a little bit of time, but I'll just show you what you should expect. So assuming that you did save the CSV to your Google Drive last time, all you need to do this time is simply run the next cell, and you should have the data from where you saved it last time. So as you guys manage to connect your Google Drive and read in the data, please drop a message in the chat so that we know where everyone's at. Everyone can just check it, that you can see Titanic data dot head so that you know your data has been read in.
Yep. If anyone is unable to see that data, just please drop in a message in the chat. Name PD is not defined. Did you run the first cell, Jacob? So you ran the first cell and then the second cell and then the third cell, and you still got that error?
Just try rerunning the first cell and see if it happens again.
Awesome. Good to hear it, Jacob. Tanaya, she says, for me, it says file not found. So this is a little bit complicated because we don't know exactly where you put the file last week. So I would encourage going into your notebook from last week and looking at what exactly the path was that you saved your file at, and then taking that path that you saved the file at and then putting it into our third cell block in the pd.read CSV line. So so if you do that, that should get you to that should get you the CSV that we cleaned out last week. Evan and Apoorv say, where can I find that file? I wasn't here last week. Varun, do you want to maybe just upload your file so for the people that weren't here last week, they can just use yours?
Yeah, that makes sense. Oh. Honestly, I can't find where I saved the file. This is probably going to take me a bit of time. So, okay, there are two things you can do. we'll send you the, in case you weren't here last week, we'll send you the link to our previous workshop, and you can pretty much run all our cells and get the data saved to your Google Drive that way. It's going to be a little tricky to find this, find the file right now. But yeah, in case you don't have it, feel free to follow it, follow the presentation for now. Right, so we have a question here about how do you log into a different Google account logged into the wrong one. So when you try to mount your Google Drive, it should show you the which all accounts. It should ask you which account you want to mount your Colab to. And that should work.
Also, for everybody that doesn't have a their file from last week, or is just unable to find it, or is having Google Drive issues, I just dropped a link into the chat that should send you to that should open up to a clean CSV file that Varun and I created. So feel free to put that one into your drive and use that one. Okay, let's give it maybe about 30 more seconds before we go ahead and get started. I'm sorry if you don't have your file ready yet, but we are under a time constraint. We want to make sure we finish on time. So we're just going to go ahead and get started in about 20 more seconds.
Don't do what I'm doing. I'm honestly just experimenting here a little bit.
Awesome. Thanks, Apurv.
Cool. Hopefully, most of you have the data. If not, feel free to talk to us after the workshop about what's going wrong. We can try to help you figure it out. For now, just try to follow along with us as we go along with the workshop. So if you see, once you read in the data, you'll have one annoying column called unnamed 0, which happens when you save a CSV file and then try to read it again for some reason. So what you can do is just go ahead and run this one line of code that would get rid of that column. And if you see that the unnamed column will no longer be there because it doesn't really help you. So now we're going to be discussing a training and test split. So we just go about what exactly this is. So the main idea of this is that when we have a data set and we want to build a model to predict anything, what we do is we say, okay, maybe we have 1,000 data points. Let's allow our model to see only 800 of those data points, or maybe 750. Let's train it with just this amount of data. And then to see how well our model does, let's try to use that model and make predictions on the portion of the data that our model has not seen. Does anyone want to take a guess at why exactly we do this? Why do we want to test our model on unseen data? Um, so essentially the reason that so we have one answer saying because you don't know if linear regression is a good fit. Uh, that's definitely true. Your model might not be a good fit at all, and so you want to see how well it does on unseen data. Uh, so the model isn't biased. That's also true. So the main reason is that if we evaluate the model's performance on just the data that it sees, it can just essentially memorize all the data. And if you show it any data that it hasn't previously seen before, then your model isn't going to know what to do at all. And that's pretty useless, right? With machine learning, you want to make use of your existing data and make predictions on new data that you haven't encountered before. So it's essentially it's important to understand how your model generalizes to unseen data. So when you may not always have this new data available. So what you do is with your existing data, you say, okay, let me split it up into 80-20, or train it with the 80% of the data, and then make predictions on the remaining 20% of the data and see how well it does. And if you get like an accuracy of maybe 70% on the unseen data, you know that in all probability, you're going to have a 70% accuracy even on data that's outside your data set. And someone mentioned overfitting. That's exactly correct. You don't want to, machine learning is about learning the patterns in your data and making predictions on unseen data. It's not about just memorizing what data you already have. That isn't particularly useful. So you want to make use of your current data and make predictions on unseen data. And that's why it's important to essentially have a train test split. So with your existing data, you essentially split it into two chunks, training and testing data. Train your model with the training data and then make predictions on the testing data to see how well you're doing. So let's go ahead and see how to do that. Uh, so just run this cell to once again import some libraries, and um, uh, let's try Googling this train test split and see how we can essentially just, oh, actually before that, yeah, let's just try to figure out how exactly we can split the data. Uh, so the first thing you can do is something like this. I'm going to drop this in the chat as well. If you run this, what it's essentially telling you is that you want to split your the Titanic data set into two groups, train and test, and you want 25% of the data to go into your testing data set, and you want the remaining 75% to go to your training data set. And after you do this, um, what you essentially want to do is you want to split up your data into X and Y. So I'm going to give you a quick example of what I mean when I say that. Um, so you want to do something like this. So what you're essentially saying here is that in your X data set, you want all the columns except for survived. So what that means is in this data set, you want P class, sex, age, um, number of siblings, number of parents, the port, and so on. But you do not want the survived column. And for the train Y, you want just the survived column. So what we're essentially saying here is that X is all your input variables and train Y is all your output variables. So why don't you go ahead and try to write a similar piece of code for the testing data. So for the testing data as well, we want to split it up into X and Y. So try so see what you can so see whether you can figure out what to do over there.
So I just see a question in the chat from Kyle. What does axis equals 1 mean? So there's two axes when it comes to a data frame. So one of the axes is the column axis, and then the other axis is the row axis, right? So when we're telling it train.drop survived axis equals 1, axis equals 1 is telling look along the column axis. So then what pandas is going to do is that it's going to go look through our columns, look for the column that says survived, and then drop that. Does that answer your question, Kyle? Awesome.
So does anyone want to drop what the code should be for the testing split?
Jacob, we're about to talk about that in just like 30 seconds, so we'll get there.
Right. So does anyone have the code for what you would do for the testing data set? We have an answer in the chat, and I think that's correct. Let me go ahead and paste that in.
Yep, looks good to me. Awesome.
So if you run these two cells, you see that train X no longer has the survived column. But if you look at, instead of train X dot head, if you look at train Y dot head, it's going to have essentially only the survived column. It does not, ignore the first column of numbers. That's just the row numbers. Right. So in train X dot head, you notice that the numbers on the left are essentially look sort of random, whereas if you look at the data set over here, you had an order like 0, 1, 2, 3, 4, all the row numbers, and over here it's shuffled. Does anyone want to guess why it's a good idea usually to shuffle our data?
Maybe to decrease the likelihood of like a bias potentially being there.
Yeah, exactly. So one problem that wouldn't we have in other answers, the algorithm won't pick up on patterns just due to the order in which the data is arranged. That's exactly right. So one very common problem that you might have is, suppose your data set was somehow arranged so that everyone who survived came first and everyone who didn't survive came later. Now, in your training testing split, if you have in your training data, you only have people who survived, and your testing data, you only have people who didn't, that's probably a bad idea. Your model is not going to generalize well. You want to have a good mix of that data in the training data as well as the testing data. So it's a good idea to shuffle it. And the thing is, when you do the train test split, typically it shuffles it automatically. And so that's a good thing, because then your training data or testing data is not biased. And we have a question here that says, is the shuffling process not completely random? My results look exactly the same as yours. That's a very good point. And the reason for that is I said something in one of these cells, I said the seed to 2. And what that means is that this is a starting point. So any sort of randomness is going to be the same for all of us. if you change the seed and rerun the cells, your results are going to look different. I kept this here so that we all have consistent results. But you can, of course, vary that and get slightly different results with no major consequences. So now we're going to address why we split our data into X and why we drop the survived column essentially. So when you're training your model, you do not want to train it with the survived column already. That's what you're trying to predict. So you're going to be training it on the X data, using the Y data, the Y data column as reference. You don't want your model to essentially memorize. You don't want your model to have immediate access to what the labels should be. Otherwise, it could just learn the labels automatically. So it's always a good idea to split your data into the input data and the output data. Right. Uh, so this essentially brings us to data leakage. Does anyone want to guess what data leakage is?
Yeah, feel free to drop your guesses in the chat or just come off mute.
Hi, sorry, could I ask you about something you just went over? I'm just having a hard time understanding it.
Yeah, for sure. Go for it.
Okay, so I know you just talked about like dropping to survive. I understand that for the training section, but just really quickly, why did you drop it again for the testing, like for the test X? I'm just confused as to why the code looks exactly the same for both.
Yeah, so essentially what we're trying to do is this will actually be kind of addressed when I talk about data leakage. So let me talk about data leakage really quick. And if that doesn't answer your question, just come back off mute and ask again. Is that okay?
Thank you. Yeah.
Okay, for sure. So let's just talk about data leakage real quick, right? So data leakage is the idea that we want to keep our training and our testing very separate, and we don't want our results to influence the data that we're training on. So what this means is, let's say that we are trying to predict, say, let's say we're trying to predict the age of somebody, right? Given like certain things about them, like what their height is, what their weight is, or and we're trying to predict their age in months, right? So let's say our training data now has a feature called age in days. So if we have a feature called age in days in our training data, and we're trying to predict age in years as our prediction, that's something called data leakage. Because what we've done is we've essentially given the answer to our prediction to our model in the training set. Because the training set will now ignore everything else, take the age in days, and just simply use that to predict age in years. So data leakage occurs when in your training data, you have some feature that directly indicates what the prediction should be, right? So that's essentially what we're trying to avoid in the code that Varun wrote. Varun, do you want to just scroll up really quick to that little bit of code? Yeah, right here. So essentially what we're trying to do here is we're trying to avoid data leakage, because we can't tell the model who has survived if we want it to predict who is going to survive, right? If we tell the model that, that's pretty much cheating and the model has no work to do. So what we do is we take our train set, right? And we take out the survived column so that the model cannot take the survived data and use that to predict who survived, right? So we take our training data, we take out the survived column, and then set that aside. We do the same thing in our testing data. We take out the survived column and store it somewhere else, because we don't want the model to be able to use this survived column in order to predict who survives. Does that make sense? Sabina, does that answer your question?
Yep, thank you so much.
Awesome. So now that we have now that we have a train X and a train Y and a test X and a test Y, we're going to try to have the model learn based on the train X and the train Y, and then predict what happens to the test X and the test Y to evaluate how the model does. So let's talk a little bit about just implementing logistic regression as a whole. So as Varun said earlier, sklearn is a fantastic library. Scikit-learn is a fantastic library that is implemented in Python, and it's going to take care of all the nitty-gritty details of logistic regression for us. So everything on that presentation, the gradient descent, the cross-entropy loss, all of that is going to be taken care of by sklearn. So let's go into exactly how to implement our logistic regression model on our Titanic data. So, I mean, Varun's been doing all the coding so far, so let me hand it off back to him.
Cool. So honestly, the hardest part about implementing machine learning models with scikit-learn is not actually coding, it's just figuring out what syntax you need. So I'm going to quickly go over, so I would encourage all of you to open up this URL on the side so that, and take a quick look at what it is. Don't need to read it in detail at all. Eventually you'll have to, I guess, but for now, just keep it open and let's see what we can do. So I guess for starters, when you import this logistic regression class, the first thing you want to do is create a model. So here you basically just say logistic regression. For those of you who are taking an intro to CS class, this is basically creating an instance of an object. I guess most of you would not have covered it so far, but don't worry about it. All you need to know is that you're just saying that, okay, my model is going to be logistic regression. Note that you've not told, this model has no information right now. It doesn't know what your training data is. It doesn't know what your testing data is. It knows absolutely nothing. It just knows that if you give it some data, it's going to try to do logistic regression on it. So this is the first thing that you would do. Basically just say logistic regression. And the cool thing is, once you know how to do logistic regression, you can pretty much do anything else. Yeah. Harsh, do you happen to have the notebook open on your end as well?
Yes, I do, but it's not going to have everything that you've typed in it. Why?
Okay, yeah, that's exactly it. For some reason, my Chrome is hanging.
Shoot. Maybe just hit a refresh, or hopefully don't lose everything you've written so far.
Okay.
Okay, I think we're good.
I think I have to run everything again. Oh wait, maybe not. Cool. Small scale. Okay, let's continue. Right. So you create an instance of logistic regression over here, and the next step is essentially training the model with your input data. And it's so easy that all the equations that we showed you in the beginning that took so long to understand, you can literally do this in one single line. And let's try to figure out together what the code should be for that. So let's open up this URL on the side. Cool. And let's scroll down here and see what the functions could be. So what you see is that if you look at all the functions associated with this class, don't need to worry too much about what exactly that means. You'll see that there's one thing called fit. And fit basically takes in X and Y. So what you can literally do is you can essentially call this function. So let's go back to the code. And you can do something like this. LR model dot fit train X, comma train Y. And what this is saying to the logistic regression model is that this is my training data. I want you to basically find the optimal weights so that I'm able to predict my labels Y. So if you just run this, you should probably run that cell first. Right. Now, if you just run this, all the complicated steps that you saw initially, where it had to find the optimal weights, then apply the sigmoid function, and so on to make predictions, this one step does that automatically for you, which is why scikit-learn is really cool. But of course, it's not always that simple. And you have an error here, so we'll address that in a second. Right. So does anyone have any questions about what we've done so far about initializing the model and then fitting it with the training data?
Yeah, let's do another quick survey actually. Scale of 1 to 5. How do you guys understand what has happened in our code so far? Cool, seeing some 4s. Good to see it. Christine says, can you explain what happened in cell 14 again? Yes, absolutely. So in cell 14, we say from scikit-learn.linear model, import logistic regression. Okay. So what is happening there is we're essentially telling Python, go to scikit-learn and get us the model in scikit-learn for logistic regression. Then we're saving that logistic regression model in a variable called LR model. So does that part so far make sense, Christine? Yep. Okay. And then in cell 15, what we're saying is LR model.fit train X and train Y. So if you guys remember, we did a quick 75-25 split and then broke that up into train X and test X. So what LR model.fit does is, yep, Jin has said it exactly in the chat. It's essentially going to train our model on our training set. So it's going to take train X, which is our labels, our features, and then train Y, which is our labels, and train LR underscore model on this training data. So essentially what lines 14 and 15 are doing is we're importing logistic regression and then training that logistic regression model using our training data. Does that make sense? Would we ever use something other than .fit to train our data? No, Advaith. In sklearn, this is a very standard format. You import your model and then you do model.fit to train it.
Got it.
And know that the cool thing is later when we do different models, while there will be some other parameters that we need to change, the broad structure is still the same. We initialize our models with certain rules, and then you can just do lr model.fit and scikit-learn handles everything for you. What you really need to understand is when to use which model. So in our workshops, we're going to be showing you 3 to 4 different models, and the broad code for a lot of them will be the same, but we do need to vary some parameters, and that's the tricky part with applied machine learning. So obviously things can't always be as simple as 2 lines of code. So you saw that when we tried to fit it through the training data, we got some kind of warning, which basically said that we failed to converge and that the number of iterations reached the limit. And it tells us that we should increase the number of iterations, max iter, or scale the data as shown in this link. So if we go back to the link that we'd opened previously, if you search for max iter, right, you see that the default value is 100, and maybe that's not enough, right? That's exactly what it's telling us. It's telling us that the number of iterations reached the limit, but we still could not find the best set of weights. So what I'm going to do is rerun the previous cell, but this time I'm going to say that max iter is equal to 300 instead of just 100, and see if this works. And if you see it this time, we no longer get an error message because with 300 iterations, the model is able to find the best set of weights for us to use, right? And yeah, that's so when you get these error messages, remember that you can always read the documentation. Try to fix the error message and rerun the code so that your model works as expected.
Yep. So just quick summary of everything that just happened right there. So essentially we got that error because our model didn't it wasn't able to train for enough time. It didn't have enough time with the data for it to converge and get a good model prediction. So what we essentially did is we increased the maximum number of iterations that the model could train for. And now because the model can train for three times longer than before, it was able to converge and is able to give us a good model and hopefully a good prediction as well.
So when you say train or iterate 300 times, does that mean that it called .fit 300 times? Is that kind of the idea that we're looking at, or?
So iterations is like, well, it's not calling .fit 300 times. Essentially what it's doing is it's calling .fit for longer, if that makes sense. So we're just giving the model more time to train the data, because instead of iterating over the training set 100 times, we iterate over it 300 times. Does that make sense?
Yeah.
The intuition to that is you're essentially saying that initially let's make a random guess for what the good weights should be. And if we do badly, let's change the weights one time to see if that makes an improvement. And if it's still not good enough, let's change it again. And let's change it 100 times until we get a good set of weights. If even after changing 100 times, we're not doing super well, maybe we want to change the weights 300 times instead. And that's essentially what you're doing with max iter. Cool. So I put these couple of lines of code on the chat. So now that we've actually trained our model, let's see how well we did on the training model itself, on the training data itself. So let's see. Let's try to figure out how we can get predictions on the training data itself. So our models learned on the training data. So hopefully we do well while making predictions. So does anyone want to guess what function we would use to make our prediction? Hint, look at the documentation. Right, so we have an answer saying predict, and that's precisely right. What we're going to do is use the predict function. So what you'd essentially do over here is once again make use of your LR model variable that has now been trained on the training data. And you're going to say, I want you to make predictions for me on the training data itself. And let's run this cell. And after this, what you can do is try to calculate the accuracy. And this is one complicated looking line of code, metrics.accuracy score. But what essentially this means is you have the actual labels for everyone in your training data. You know whether they survived or not. And this is what your model is telling you. Your model is telling you what it thinks about whether these people survived or not. And if your model is trained well, this should be quite close to each other. And so if you run this cell, it says that the training accuracy is 0.796, which essentially means 79.6%. So that basically means your model has learned to classify 79% of the training data correctly using logistic regression. So, okay, once again, does anyone have any questions on what predict is doing and what the accuracy over here is?
I'm confused as to why we're not using train X test X and test Y instead of the train X and train Y for the predictions.
Yeah.
Great question, Cameron. So we're actually going to use test X and test Y in the future because we want to see, of course, because what matters most is whether or not our model is able to evaluate data it hasn't seen yet. But before we do that, it's always a good idea to see how your model is doing on the data that it has already seen. For example, if your model is getting like a 20% accuracy on your training data, there's no point of even looking at how it's going to do on the testing data because it's already doing so poorly on the training data, right? So, for example, like let me give you an analogy. Like if you're doing badly on your homework, you're probably gonna do really bad on the test, right? So if you're doing bad on the homework, there's no point of even seeing how you've done on the test because you're likely to do really bad on the test because you've done badly on the homework. But if you do really well on the homework, now we should go ahead and take the test and see how you do on the test because we know you have the skills from the homework. Does that make sense?
Yeah, thanks.
Awesome.
So we have a question that says, what does normalize equal to true do? I guess the default value is normalize equal to true, but if you make this false, it basically says 530. This means that if your training data had a certain number of examples, then you got 530 of them correctly. And when you make this true, it essentially divides by the total number of training examples that you have. So it's more useful to get something like 79% instead of saying you got 530 examples correctly, because it could be 530 on 10,000 or 530 on just 1,000. Yeah, it turns it from a count into a percentage. That's exactly it, right? Okay, cool. So this part's a little complicated. So let's revisit this cell later. Let's look at the next cell. Test y pred equal to an accuracy equal to. So let's try using similar code from here and essentially trying to figure out what the test prediction should be and what the test accuracy is. Let's take a minute. It's essentially the same code. So if anyone wants to drop in the chat what they think the answer should be for this particular cell, let me know. Does everyone understand what we're trying to do over here? Okay, so the idea is that over here, we trained our model on the training data, and we want to essentially predict what the accuracy on both the training data and the testing data should be. So what we would do is that this is how we got the accuracy for the training data. So now we're going to be doing the exact same thing for the testing data as well. So we would do something like this: LR model dot predict on test X, and we're going to have essentially the same line of code, except this time we don't want to compare train Y and test and the train Y prediction. We want to compare test Y and our test Y prediction. So what this is doing is we want to predict how well our model is doing on the unseen data. And here we see that we're getting an 82.5% accuracy, and that's really good, especially considering that our training accuracy was only 79%. Our testing accuracy is slightly better, Now, normally, this is not something you would expect. You would expect your testing accuracy to be lower. We just happen to get lucky this time. But usually this is going to be a lower number. But what this means is we've done a pretty good job. We're getting roughly 80% accuracy on both the training data and the unseen data. And what this means is our model has not just memorized the data itself, but it's understood what the pattern of the data is. So it's using that same pattern to make predictions on the unseen data. And we're getting roughly an 80% accuracy. Right. So let's go ahead and look at a couple of other metrics. So what we're going to be doing here is, Harsh, do you want to explain what this is about?
Yeah, sure. So essentially what we're doing here is so Varun has this code here, so you can see precision is blank and recall is blank, right? So essentially what we're trying to do is we're trying to look at different ways to potentially evaluate this model. Right now, the only thing we have is accuracy, right? But accuracy isn't always the best way to evaluate a model, right? For example, let's say you have a model where you're trying to predict whether or not lightning will strike on a certain day, right? So lightning, if you're in California, maybe strikes like 1 or 2 days out of the year, if that, right? So if you look at the training data, 99% of the time, lightning doesn't strike, right? So if you have a model which just simply guesses that every single day lightning won't strike, that model will be correct 99% of the time, because on 99% of days, lightning doesn't strike. But that model isn't actually doing anything complex, right? All it's doing is that it's saying no every single time, and it just happens to be right 99% of the time because that's how the data is distributed. So instead of using accuracy as a metric, we can use a different metric, for example, precision, or we can use a different metric such as recall. So what precision and recall are is it's true positives divided by true positives plus false positives. So a true positive is when something happens and we predict that it actually happened. A false positive is when we predict that something happened, but it doesn't actually happen. And then on the other hand is recall. Recall is true positives divided by true positives plus false negatives. So false negatives is when we predict that something won't happen, but it actually does happen. So these are just different ways of evaluating your model, and they're just two different metrics that you can also look at when evaluating your model. If my explanation of precision and recall didn't make a lot of sense to you, don't worry. We're going to go into precision and recall in a little more detail in an upcoming workshop. We just wanted to give you a quick taste of it right here.
Cool. So I guess to reiterate the main point, the main takeaway from this is that we've trained a model with our training data, and we're getting roughly 80% accuracy on the training data. And we're able to use this model and make predictions on unseen data. And on the unseen data, we once again have a pretty high accuracy of roughly 82%. And so that's pretty cool. We essentially have a model that has an 82% accuracy. But there might be there's a different way of evaluating the performance of your model. So one thing you could do is, so here, for example, we split our data into 75% training data, 25% training data, trained it on that 75%, and saw what our performance was on the test set. Now, like we went over before, it's a good idea to shuffle your data, because if there's some inherent bias in how you split your training and testing data, you might not get a very good model. So it's better to shuffle it. But it's also possible that your shuffling wasn't great and you just happen to get lucky with your testing data or training data. And so another good idea to evaluate your models, to evaluate whether what you're doing makes sense, is something called k-fold cross-validation. And this is a very fancy sounding term. But what it essentially means is, let's say I have 100 examples. I split up my 100 examples into maybe 10 groups of 10. Um, and what I do is I first train my model. Uh, I first train my model on 90% of the data and then make a prediction on 10% of the data. And Harsh is going to explain why something like this is going to be useful. Yeah. So Harsh, do you want to take over and explain why exactly we need something like cross validation?
Yep, sorry about that. I was talking, but I was on mute. My bad. So just to give you guys a quick visualization on what exactly k-fold cross validation is doing, Varun, if you could run that cell for me right there. That should bring up a quick picture. Awesome. Okay, so all right, looks like we can't fit the entire picture onto the screen, but we're going to do our best. So here's what we're doing in k-fold cross validation. So if you guys remember earlier on in the workshop, we did a 75-25% split between our training data and our testing data. Then we trained on that 75% training data, and then we tested on that 25% testing data. But that was only one potential configuration, right? So let's take a look at what's happening in this picture here. So here, what they've done in this picture, they've divided the data set into 5 sections. So you can see in that first row, there's like 5 boxes, right? And one of those boxes is in a blue color, and the other 4 boxes are in a gray color. So what we're doing is we're going to take these 5 boxes, assign one of them to be a testing box and the other 4 to be training boxes, right? So the data in the 4 training boxes will be used as our training data, and the data in our 1 testing box will be used as our testing data. So we will, in this first configuration, we'll first train a model and then get its performance. Then instead of using that first split of data as our testing data, we'll use in that second row, we use our second box as our testing data, and then our other 4 boxes as our training data, and then so on and so forth. You can see in the third row, we use the third box as our training data, and in the fourth row, we use our fourth box as our training data. In the fifth row, we use the fifth box as a training data. And then we train 5 separate models on each of these different folds that we have. And then at the end, we aggregate the performance of these 5 models and essentially take an average to see how our model is really doing. So essentially what k-fold cross-validation gives us is it gives us a way for us to train more models and get more out of our data, even if we have a smaller data set. And k-fold cross-validation is a really good way to evaluate your model and make sure that it's able to learn from different chunks of your data. For example, it's very possible that when you were training, you got some chunk of data that was very strange, had a lot of outliers in it, and your model learned something very strange from that data and didn't test well. But maybe in other folds, it missed out on that strange chunk of data and was able to generalize well. So k-fold cross-validation can really help you kind of diagnose your model and see what sorts of issues it has. And it can also show you whether or not your model is generalizable and is able to perform well on different folds of data. So we have a question in the chat. Can you also shuffle data between the boxes? So no, you would not want to shuffle the data between the boxes, because the point of k-fold cross-validation is giving your model a different chunk of data, like a different distribution of training data every single time. Will we ensure that all 5 models are independent from each other? Yes, all 5 models are independent from each other, because there will be a different model trained on each of the folds. I noticed the term validation fold is used. Is this different than testing fold? Yes, it is in a way. So I guess quick aside, what often happens in machine learning fields is when you're like first starting with ML, you're only introduced to training and testing as your like 2 divisions. But as you progress, what is actually used in industry is training, validation, and testing. So for now, you can consider validation and testing to be the same thing. At this stage, it's pretty much the same. But just know that as you progress in machine learning, validation and testing do end up being a little bit different in the future. But for our purposes here, you can treat it as the exact same thing. Won't the model be different in each iteration? Yes, Cameron. In each iteration, the model will be slightly different because it's being trained on different data. That's why in order to see the performance of all of our models as a whole, we average out the performance at the end. As you can see on that right side, we're doing 1 divided by 5 times the sum of all the performances. After doing all this, when you actually use the model to predict with new data, is the model trained on all the data or with one specific train test split? Kyle, that's a fantastic question. So k-fold cross-validation is only used to kind of see how your model is doing and to evaluate performance. It's not something you actually do before you like put a model into production. So the model would actually only be trained on one specific training or testing split before you put it into production. The point of k-fold cross-validation is just really to validate your data, to validate your model and make sure it's doing well. Any other questions? Feel free to pop them in the chat or just come off mute.
Yeah, just to build on what Harsh said, K4 cross-validation isn't to check whether your particular logistic regression model is doing well. It's about finding out whether logistic regression in general is a good choice to use for your data. So you can think of it in some sense as doing what we did before, just doing a train test split, and doing it 5 times with random shuffles and averaging out the results to see how well we're doing. So you would, like a couple of people brought up, that you won't actually be deploying all the 5 models that you train in this case. You'd be deploying only one of them. This is just to ensure that you didn't happen to train your model on some bad split of the training and testing data. And yeah, that's essentially it. As you have more data, I guess this becomes somewhat less important, but this is always something you can do to evaluate your model's performance. Right. So now let's go ahead and see how you would implement something like k-fold cross-validation. The code does look a little messy, but let's see what we can do.
By the way, while Varun is writing the code in, can you guys just drop a quick 1 through 5 in the chat on how you guys feel about the concept of cross-validation and if it makes sense to you or not? Awesome. Seeing a lot of 4s. Seeing 1 5. Shout out Advite. Cool. Good to hear. Cool. So one of the great things about scikit-learn is all of these like core machine learning concepts that we're going over, like logistic regression, training testing split, k-fold cross-validation. Scikit-learn pretty much takes care of all of these things for you. So if you want to, run k-fold cross-validation on your data, it's actually really, really easy with scikit-learn. And that's what Varun's going to show you right now. He's putting the code in as we speak.
Now it's a huge chunk of code, and you're definitely not expected to understand this in your first try. So let's try to slowly walk through what it means. Right. So firstly, we just import the k-fold library from sklearn, and similar to what we did before, we use the entire data set, not a training testing 75-25 split like we did before. We use the entire training data set and create the X and Y data sets like we did before. And now what we're essentially doing is 25 is too much. Let's make this 5. We're saying let's split up the data into 5 groups like you saw in this picture here. And what this code is essentially doing is saying that, okay, when we do kf dot split this line for train index comma test index in kf dot split, it's essentially saying that in the first case, we're going to have, this is our training data and the blue box is our test data. In the next iteration of the for loop, our training data is automatically going to be this, these 4, and this is going to be our testing data, and so on. So that's what this for loop is going to be doing. So at every single time, you have a new training data and a new testing data. And every single time, you essentially repeat the same code. You create a logistic regression model. You fit it with that particular training data and testing data. So I keep going back to this picture. So the first time you're going to be training on this and testing on this. The second time you're going to be training on these 4 blocks and testing on this, and so on. So that's exactly what's happening here. We first have our new training and testing data. Then we train our data on this model. And after that, what we do is measure the accuracy like we did before, where we essentially predict on the training data, get the accuracy. Then we predict on the testing data, get the accuracy on the test data. And we keep storing these accuracies in an array. And at the end, what we can do is print the mean training error and the mean training accuracy and the mean testing accuracy. So let's just see what the output looks like. So what this essentially means is that we're essentially training 5 different models, and the average training accuracy across those 5 models is 79.58%, and the average testing accuracy happens to be 79.97%, which is pretty similar to what we got before, where we got 79 and 82%. So we see that in first case, we did in fact get a little lucky. Our testing accuracy was 82%, when actually when we do an average across 5 different splits, we only get 79%. So that basically highlights why you would do something like k-fold cross-validation, to get a better estimate of what your testing error should be. So I know this was a lot to take in, and honestly, it's unreasonable to expect you guys to understand this immediately. Just know that something like k-fold cross-validation can be done, and if you ever encounter a case where you need to use this, it's just so that you know what k-fold cross-validation is, and if you ever need to use it, you know what needs to be done. Right. So
let's take a moment here and just stop for questions real quick, because I know we just plopped a lot of code on the screen here. So if you have any questions, put them in the chat or come off mute.
I'm just going to put this code on the chat so that you guys can do what I'm doing.
Varun, I think you might have to put it in 2 sections, because I think there's like a character limit on the Zoom chat or something.
Oh, okay.
I had a quick question. So I assume with k-fold that you would only get one set of accuracies. Why is it that you have like a training accuracy and a testing accuracy if you only are looking at like the testing? Because you only like take one in each model, right, of the 5?
Right. So do you remember the process we just went through earlier before we got into the k-fold cross-validation? We did the training testing split, then we saw our training accuracy, and then we saw our testing accuracy.
Mm-hmm.
Yeah. So with k-fold cross-validation, we're essentially just doing that over and over again, except for every single iteration. So for every iteration, we change what the training and the testing set are, and then look at the training accuracy and the testing accuracy again. Does that make sense?
Oh, I see.
Yeah.
Cool. So that's pretty much what we had for this workshop. And I guess the one main thing that we'll do next workshop is ensure that anyone who wasn't there for the first workshop has access to the clean data. So
Yep.
in case you weren't able to follow it completely this workshop, don't worry. Next time we'll ensure that you have access to the data right at the beginning, so you can follow along. We'll also be posting this workshop video on YouTube soon. So in case you didn't understand something completely and you want to go over it again, you should be able to. Once again, this is a new workshop. This is the first time we're doing it. So if we got something wrong, if we did something well and you want to see something like that again, please let us know in the feedback form over here. It's really helpful to understand what exactly you guys thought went right and what went wrong, so that we can keep improving our workshops. So please fill out the feedback forms so that we know what we're doing. And yeah, I hope you guys learned something new and you're excited about applying machine learning.
Varun, I think Kyle might have just found a small bug in our code.
Yeah, why does the first training accuracy score line use train Y instead of train YK? Very good point. That is
Good catch, Kyle.
Yeah, and that was actually a pretty big mistake. So you see that our testing accuracy is actually a little lower than our training accuracy, which is what you would normally expect, because you typically don't do as well on unseen data. So yeah, good catch, Kyle. Thanks about that. Yeah, are there any other questions? Any problems that you guys faced? You're still not sure about?
Oh yeah, question from Advite. I'm sorry, I completely missed that. How would you decide what n_ splits should be? I feel like there's no really hard and fast rule. I would try to keep like the number of splits so that you have a decent amount of data in both your training and your testing sets. I wouldn't go too big on it, because if you have like a lot of splits, that just means each split is very similar to each other. So there's no real point of the k-fold cross validation. I think it's tough to say really, because it really depends on the size of the data set you have. For example, if you have a really large data set, you'd probably want to use more splits. If you have a smaller data set, you'd probably use less. So I know that's not the answer you're looking for, but there's no really hard and fast rule to decide the number of k-fold splits you'd use.
Gotcha. No worries. That makes sense.
For sure.
Where do we change the train Y to train YK? Yeah, so in this particular line, there was a bug. It was just train Y. It should be train YK. And train YK pred as well.
Cool. If you guys have any questions, like feel free to stay on or put them in the chat or ask. Like Varun said, we really appreciate it if you guys could fill out that feedback form again. We read every single response that you guys put in last week, and we really tried to tune this workshop to, try to address some of the concerns you guys had. So, like you said, this is the first time we're doing this. So any feedback that you give is very helpful and very valuable. Besides that, though, if you don't have any questions or feel free to go. That's pretty much all the content we have for you guys. Yep, no problem, guys. We love doing this, and we love seeing that it's helpful for you guys. So, yep, I'll see you guys next week. Thank you. Marissa, I think you were messaging me earlier regarding a bug you have. Do you want to just come off mute, maybe share your screen, and we can try and work through that bug together? And also, Varun, you probably want to stop the recording now too.
Yeah, let me do that.
How should we find the values for precision and recall? I think I dropped in